Okay, so welcome everybody. As I said in chat, if something's wrong with the audio, let me know because I haven't used this headset before for streaming anyway. So I don't know how how the mic sounds. So you'll have to let me know if there's some problem because I was using the same old cheap headset all spring, and so I had to mess around with the settings, and I'm not sure exactly how this thing is. How this thing sounds. So anyway, so welcome. This is typically, how you're going to get the lectures. I'm just going to, so they're unlisted while the live stream's going on, and that's just to prevent. Like I noticed that when you get like above a certain threshold, it's usually about 40, so it shouldn't be a problem for this class, but I didn't even want to test it. When you get above a certain threshold of live viewers on YouTube, it like the way that the algorithm kicks in is it like blasts your live stream to like a bunch of random places. And so when I get to like a threshold of like 40 people watching at once, if it was public, then it would get blasted all over the place, and I would have like a ton of random people joining in. So it was better to do it this way. So it will immediately be made public on the YouTube channel, so that you don't have to access it through Elms or anything. You can just use the YouTube channel. So right after this lecture ends, I'm gonna set it to be public, and it should be uploaded pretty much immediately after that. Sometimes it takes a couple hours, but anyway. So that's how it goes. So typically, like 5-ish minutes before lecture starts, I'll post the link on Elms. This time I wanted to do it a little bit early just to make sure that everything was going well. In the event that there's some internet issues that inevitably come up, like during when I'm supposed to be live streaming, then I will just either record it later uh, or I will break it up into parts, depending on how it happens. That's what I did over the past couple semesters. So anyway, that's that. I haven't added anything to the syllabus page yet, so I'll do that later today, but there's not too much to say here other than your grade will be determined entirely by homeworks. Uh, so the homeworks, this is a summer class, so obviously it's a lot denser and more intense. So we'll say roughly 2 per week. It won't always be 2 per week, but it will be roughly 2 per week. The format here is going to be, you're probably used to this by now, having a few semesters of online only, but basically you're going to do your homework and upload it as a PDF and submit it on Elm. So I'll have columns where you can submit the homeworks. Like I said, about 2 per week, so roughly like 10-ish total. It probably will be more like 9, but it's okay. So like 10-ish total homeworks. The homeworks will either be selected from the textbook, and so I posted a copy of an older edition of the textbook. Wherever the homework gets posted from, either I will write it and post the problems, or I'll write some of the problems and post them, and otherwise I will submit the problem list that the homework comes from. Okay, so you will be provided the problem list one way or another. Exams, so there's going to be 2 midterms. Um, so the first midterm is tentatively June 18th. Now I know that although this isn't included in the academic calendar, apparently there's no classes on June 18th, but that won't affect me assigning the midterm. The format of the midterms is going to be I'm going to post it, and then you're going to have a couple of days to do it and submit it. Okay, so the midterms are kind of like they're kind of similar in format to the homeworks. They're just going to be well, I don't know if I would call them harder, but they will be different. Okay, the midterms will be different. The problems I select for the midterms will be slightly different from the homework problems, obviously. So anyway, so you're going to have 2 midterms. Like I said, first is approximately June 18th, which is in a couple weeks. Next one will be roughly 2 weeks after that, and then you will have a final exam, which will be cumulative. So cumulative and cumulative, I think I spelled that right. And it will cover everything. Of course, it's a little funny because summer class is only 5 weeks, but it just allows me to put kind of a smattering of problems from all over the course in this thing. Okay, so the course content. This is going to focus a lot on the computational aspects of complex analysis or complex variables. There will be some, I will include some derivations and proofs of things that I may ask you to do, especially since we're remote only, so you have a little bit more time to be a little bit more maybe thoughtful on some of these assignments and exams. So maybe some kind of proof or derivation that wouldn't have made the cut in an in-person exam would be something that I might give you to do in this class, since you have more time to think about it. But anyway, anything else I can think of off the top of my head? So as far as anything that wasn't covered in the original announcement, there was an announcement made, I think, yesterday about the tutoring schedule, so I will expand on that. I'll include that in the syllabus as well. So there's, I believe it's daily Zoom tutoring. You can see the announcement for that. And I haven't added the Zoom tab to the course yet. You can still access it through the link that was in the announcement, but also I can add a little Zoom tab to the Elms page that you can access it directly from that. So either way, doesn't matter. You have to use your official UMD Zoom account, I believe, for that. Anything else I can think of off the top of my head? I think that more or less covers it. If you all have any questions, you can let me know. You can just type them into chat, and I will answer them. Any general questions about the course, but I think that covers us for now. So I'll assign a homework like tomorrow-ish, and it'll be due in a couple of days, and so that's kind of how our homework schedule is going to be. Like I said, I'll try to keep it to 2 per week. So it's going to be, well, you know what you are getting into with the summer course. You know that it's a lot quicker, a lot more dense. So so you know how it is. Anyway, all right. So let us start with the basics. So if I want to talk about complex numbers, first of all, why do I want to talk about complex numbers? So the kind of the easiest context, right, in which you first saw complex numbers or imaginary numbers was in just solving some basic algebraic equations. Typically, when you first discuss quadratic equations or finding roots of quadratic polynomials, complex numbers enter in. And of course, you could view complex numbers as being introduced in the same way that you introduce negative numbers, right? So the idea is if you're looking at some basic equations, right? So if you have an equation like, I don't know, like we'll say, right, like 5x. No, let's start with something here. Let's start with something like this, right? So if I have the equation like x minus 2 is equal to 0, right? So to solve an equation like this, right? Well, I know what solves an equation like this, and it is fine if I have just natural numbers only, right? So natural numbers only, it solves an equation like this. So if I have x minus, a is equal to 0, and a is a natural number, we'll say. So natural number here, these are, natural numbers are 1, 2, 3, so on, right? Counting numbers. Okay. Then I have an equation like this. All I need for solutions to an equation like this are natural numbers, right? That's it. And so, okay, that's fine. I don't have to think too hard about that. But the second that I have maybe an equation like, say, this, okay, well now natural numbers aren't going to cut it, right? I need more than that, I would need rational numbers, right? I need fractions. Okay, if I have an equation like this, right, now natural numbers aren't going to cut it anymore. I need negative numbers. Okay, and so if I have an equation like this, if I want to talk about solutions, and I don't just want to dismiss them and say, oh, it doesn't have any solutions that I'm interested in. If I actually want to talk about solutions to something like this, well, real numbers aren't going to cut it, right? So I have to adjoin something else to the real numbers to talk about solutions to equations like this. And so complex numbers are introduced in this way because they let you keep going, right? They let you talk about solutions. They're convenient. And it turns out, of course, that they're not actually too off the wall, right? In fact, you have already encountered them. Even if you've never heard of complex number in your life, at this point in your math education, you know about points in the plane, right? So if I have some point xy in the plane, okay, you have seen this over and over and over again, but of course this is exactly what we're going to use to define complex numbers in the first place. And so what is a complex number? We identify a complex number z. So the set we use to denote complex numbers is this c bar, okay? And so a complex number z is an ordered pair of real numbers, okay, that I can think of as just a point in the plane here, right? Okay, so how does this work? What's the difference between a complex number and a point in the plane? Well, algebraically, we're going to see that there's not one, right? So in a certain way, this description of complex numbers is going to be exactly the same as my usual description of R2, right, the Cartesian plane. And so if you remember from, say, a linear algebra course, or if you've heard this language before, we can say that there's a notion where this set C of complex numbers and this set R2, the Cartesian plane you're used to, are isomorphic, or they are the same algebraically. Or another way of thinking of them is that the complex numbers are rather the real plane is like a relabeling, right, of the set C. Now, when I say that a complex number is an ordered pair here, what do I mean? Well, it consists of two parts here, a real part and an imaginary part. Okay, and so we would say that the real part of Z is X, and the imaginary part of Z is Y. So I'm going to write that in words. This is real part of Z is X, and this is imaginary part of Z is Y. Now, of course, the imaginary word is coming in historically, right? The complex numbers are called imaginary numbers. Of course, it's kind of a funny way of thinking about it because, in a sense, right, most of the numbers you've ever encountered are imaginary in some way, right? I don't want to get into a philosophical discussion of whether or not numbers are real, or whether we're talking about like the Platonic form of numbers or something. But if you really believe that an ordered pair xy is the same as a complex number, and that's how we're going to treat this, then if you think that a point in the plane is real, right, then an imaginary number is just as real as, well, a point in the plane, right? So anyway, so this note that both the real and imaginary parts of a complex number are real numbers, right? X and Y are real numbers, so both of these are real. And so we are going to entirely think of complex numbers as being represented in this way. Now, you might be asking yourself, well, wait, when I first dealt with complex numbers, I didn't necessarily see them in this form. I saw them in the form complex number is x plus iy, where x and y are real numbers. And we're going to see exactly what we can do with this, okay, in order to have this interpretation be exactly the same as this, more familiar form here. So I'm going to redraw my complex plane here. And so redrawing my plane, I have, so xy, this is some generic complex number z. Okay. Well, note that we have numbers like, say, here's a number, we'll say 5, 0. Well, if any point in this plane is a complex number, then this is 1. Here's another one. Right, 0, 1. Okay. And so if we look at 5, 0 here, then the real part, right, so the real part of, if we call this, say, z sub 1, and we call this z sub 2, then the real part of z sub 1 is 5, and the imaginary part of z sub 1 is 0. Okay, and for this one, the real part of z sub 2 is 0, and the imaginary part of z sub 2 is 1. Okay, so these are just two examples of complex numbers. So in this case, we have complex number that has a non-zero real part, but a 0 imaginary part. And then we have the opposite thing here, where z sub 2 has a 0 real part and 1 for its imaginary part. So such numbers might be called purely imaginary. Okay, so purely imaginary is a term you might use to describe a number like this. So following exactly that terminology, you might use the same way of describing this. You might call this like purely real. Okay, but it turns out that purely real really just means real, right? And so this is going to show us, and we're going to see when we first define operations here, that the real numbers actually sit inside the complex numbers. And they sit inside the complex numbers as the x-axis. Okay, and so if numbers like this are actually just my real numbers, then maybe I'll write that up here. So the real numbers sit inside C as the x-axis. Okay. And so what this means is that any real number can be thought of as a complex number. Okay, and so the complex numbers are, in a sense, an extension of the real numbers. Okay, and this extension is exactly thought of if you think of the x-axis as being the real number line that you were introduced to many, many years ago, then the complex numbers is just adding another number line, another axis to that picture. Okay. And so we want to discuss algebraic properties here. So algebraic properties of the complex numbers. Now I'll return to this in a second, but the first thing I wanted to note is, let me bring back my picture here. So there is something that you might notice immediately about complex numbers, right, if we're thinking of them as points in the plane. So first of all, what does it mean for two complex numbers to be equal, right? So what does it mean for z1 and z2 to be equal? So z1 and z2 we'll take to be complex numbers. Okay, in general, when I write z with a subscript or when I write a z, you can expect that to be some complex number. But what does it mean for two complex numbers to be equal? Well, if I come back here to my picture, two complex numbers z, so if I have, say, z sub 1, that's x sub 1, y sub 1, and I have a z sub 2, that is x sub 2, y sub 2, they are equal when they occupy the same point in the plane. Now, this is exactly the same as the notion of equality on the real number line, right? How do you know that two real numbers are equal? Well, if you think of the real numbers as being a number line, they're equal when they occupy the same point of the real number line, right? So similarly, these are equal when they occupy the same point. But what does it mean if they occupy the same point? If two ordered pairs in the plane occupy the same point, if they're actually the same ordered pair, it means that x sub 1 and x sub 2 are equal, and y sub 1 and y sub 2 are equal. So it means that their real and imaginary parts are both equal, right? That's one way of interpreting this. So what does it mean for z1 and z2 to be equal? Both their real and imaginary parts. It's got to be both, right? It can't be one or the other. So both the real and imaginary parts are equal. Okay. All right, so that's not too confusing. But you're talking about equality of points in the plane. That naturally brings up another question of, say I have two complex numbers, z sub 1 and z sub 2. Right? I know what it means for z sub 1 and z sub 2 to be equal, so here are two complex numbers that are not equal because they occupy different points in the plane. Okay, but can I say anything about the relative position of these points? Right? What am I asking here? Well, let's go back to the real case for a second. When I have real numbers, right, on the real line, here's two unequal real numbers. We'll say x sub 1 and x sub 2. Right? Maybe here's a reference point, 0, so both of these are positive. Okay, so when I have an arrangement of points like this, I can make some statements here. I can define a notion of inequality between these points. So there is a notion of, so in this picture, we can say that x sub 1 is less than x sub 2. And in fact, both of those are greater than 0. Right? And of course, I can continue doing this, right? So 0 is greater than, for instance, minus 5, which is greater than minus 50. Right? Maybe here is like 21, right? So these are less than 21. There is a notion of ordering on the reals, right? So one early thing to caution against is when you have ordered pairs, well, what would it mean to say that z sub 1 is less than z sub 2, or that z sub 1 is greater than z sub 2? What would those things mean? Well, it turns out they wouldn't really mean anything. Right? We don't really have a notion of that for ordered pairs. Okay, and so we're not really going to have a notion of complex numbers being greater or smaller than some other complex number. Okay. Now, there is a way that we can get around this, and we can still talk about a notion of size for complex numbers, but we can't do it with just the numbers as they show up themselves, as points. Okay, so we were able to do that for real numbers, but we're not able to do that for complex numbers. So that's one key difference already. Okay, but I want to know algebraic properties of C, but of course I'm talking about algebraic properties, I need algebraic operations. So then what are those? Well, when I have algebraic object, it is nice, of course, to define algebraic operations. So, or rather, I should say that an algebraic object is an algebraic, oh, what am I doing here? This is x sub 1, y sub 1. This is x sub 2, y sub 2. It's the algebraic operations that make something an algebraic object, right? So if I, say, want to discuss adding these two things, okay, then how would I go about that? Well, so when I use this, it means that I'm defining what follows to be z1 plus z2. So if I want to add two complex numbers, how do I do it? Well, the complex number that results is the, what is this? So the complex number that results is x sub 1 plus x sub 2, y sub 1 plus y sub 2. And that is to say that I add the real parts, I add the imaginary parts. And so the real part of this sum is the sum of the real parts of z1 and z2. And the imaginary part of the sum is the sum of the imaginary parts. Okay. All right. I also want to define z sub 1 times z sub 2. Okay. So how does z sub 1 times z sub 2 work? This is defined to be x sub 1 times x sub 2 minus y sub 1 times y sub 2. In the first slot, and the second slot is y sub 1 x sub 2 plus x sub 1 y sub 2. Now, the first one, you might say that's totally intuitive why you would define the sum of two complex numbers to be that, or the sum of rather two ordered pairs to be that. But this second one, why would you define the product of two ordered pairs to be this weird thing? Okay, so we're using a little bit of backwards thinking here. Okay, and the backwards thinking that we're using is we are treating these, right, as x sub 1 plus I, y sub 1, and x sub 2 plus I, y sub 2. And we're multiplying them using this I squared is equal to minus 1 fact, or that I is square root of minus 1, the imaginary unit. I'm going to bring all of this stuff back into the fold, okay? But that is the motivation for where this comes from, okay? But if you forget that for a second and just say, these are the definitions I'm going to use. So I take the plane, right? Ordered pairs in the plane, and I take these two operations of plus and multiplication, right? So sums and multiplications are defined this way. Then the algebraic object you get out of that is the complex numbers. Okay, that's the complex plane. Okay, and so of course the reason for this weirdness here comes from algebraically expanding these terms multiplied together and using this fact here. Okay. All right, so like I said, we're using a little bit of backwards thinking. You might notice that if z1 and z2 are just real numbers, right? So note if z1 and z2 are real, well, if they're real, oh, I'm a little bit off screen. If z1 and z2 are real, then what would they look like? They would look like x sub 1, 0, that would be z1. And z sub 2 would be x sub 2, 0. So if they're real, then when we sum them, we get x sub 1 plus x sub 2, 0. And when we multiply them together, I'd have x sub 1, 0 times x sub 2, 0. What would I get according to this formula? So all the y sub 1 and y sub 2 are 0, so that's 0, and that's 0. So what I would get is x sub 1, x sub 2, 0. What does this say? This says that if you have real numbers and you use these formulas to define addition and multiplication, this is just normal addition and multiplication of real numbers, right? So this is usual multiplication and addition of reals. And so this is what I mean when I say that the complex numbers are an extension of the reals in this way. Okay. All right. Now, here is where I finally bring back this, maybe more intuitive way of thinking about complex numbers. Right? This is to show you where the structure comes from. Of course, now, if I take a generic complex number, okay, and I think, okay, generic complex number is this. Okay, so generic complex number is this ordered pair here. Well, using my definitions of addition and multiplication on the previous page, okay, I can actually notice that really this is x0 plus, right, 0 y, if you like. But I can write this in a slightly different way. Okay, I can actually write this as x0 plus 0, 1 times y0. Why does this multiplication work out to be that? Well, again, I'm using this to multiply my ordered pairs here. All right, so if you work through this, what do I get here? I would get, so this is going to be, so z2 is 0, y here, so this is going to be 0 in the first slot, and it's going to be y in the second slot, because it's going to be y1 times x2, which is going to be y here, right? So this is 0, this is 0, this is 0, this is going to be y times, or sorry, this is going to be 1 times y. So it's going to give me exactly that. Okay. Okay. Why do I want to write this? Well, notice that x0 that's a real number, right? Because it's purely real, right? It has 0 for its imaginary part. y0 is a real number, right? Again, for the same reason. This is a purely imaginary number, 0, 1. I plotted that on our plane before. So if I let I be defined to be 0, 1, then another way of writing this is x plus I, y. Okay. And we can check, I won't do it here, but you can check using that same, those same rules for multiplication here. Check that I squared is equal to minus 1. So multiplying I by itself gives you the real number, minus 1. Or, written another way, right, if we allow ourselves to take square roots here, or to think of this as a square root, I is the square root of minus 1. This is our imaginary unit. it is the I that you've been familiar with all this time in the context of complex numbers. Okay. All right, and so this explains what it is that's going on here. All right. So if you want to see, right, like what is I squared? Right? I squared is 0, 1 times 0, 1. Using our formula, let's bring it back. Okay, so x1 and x2 are both 0. Okay, so this term is 0 times 0. All right, so that's 0 times 0 minus y1 times y2, which is minus 1 times 1. Okay, and then in this slot we would have 1 times 0 and 0 times 1. Right. And so this is minus 1, 0, which of course is just the real number, minus 1. Okay. So yeah, that starts a nice, you'll notice that in this course, several times you will hear me say I'm not going to do it, and then I'll just do it. That's kind of a habit that I have. So, so this is the first instance of that in today's lecture. First instance of the course of that happening. Okay, so now we have this identification, right? I can think of an ordered pair xy as being represented as my favorite form of complex number at the moment, right? Which is x plus iy. And so I could actually reformulate exactly those algebraic rules for adding and subtracting these things. So if I think of adding two complex numbers, I'd have x sub 1 plus I y sub 1 plus x sub 2 plus I y sub 2. Of course, after rearranging, pulling out the I here, right, doing a little bit of cleaning up here, this is the real parts summed plus I times the imaginary parts summed. Okay, of course, the real place that this shines is in giving us a nice, easy algebraic way of seeing why the formula works out the way it does for multiplication. When I multiply these, I would use the fact that I squared is minus 1 here, right, to say, okay, right, so the point is that I'm actually translating the definitions here into this new language, but you could view this as, pretend you go back to like Algebra 2 in high school or middle school or whenever, and you look at this, and I just ask you to expand this using the fact that I squared is equal to minus 1. You're going to get the exact same thing, right? You're going to FOIL this out, right, or distribute this, however you want to do this, and you're going to get exactly what you think here. So IY1, IY2 multiplied to get I squared, so that's where the minus sign in the first slot comes from. So this is x sub 1 times x sub 2 minus y sub 1 times y sub 2, plus the mixed terms I can pull the I out of, and so this is I times y sub 1 x sub 2 plus y sub 2 x sub 1. Okay, and so there's our favorite form showing up in this definition. Okay. All right. And so other basic properties. Notice if z is any complex number xy. So if I say nothing else, we'll always assume that it's of this form to save me writing this notation over and over again. If I multiply z times 0, then what do I get? So multiplying by 0, that's here. 0, of course, is, so this would be x, y times 0, 0. Okay, since the origin in the plane does in fact lie on the x-axis, right? So 0 here is just my ordered pair 0, 0. And of course, what do I get when I do this multiplication? I get 0, 0 And so that's just 0. So multiplying any complex number by 0 gives you 0, just as it did for reals. Okay. So it might seem like we're really, being meticulous here on picking out all of these, but I promise there's a point to being this way, because there are some differences, right, that are going to come up very soon. There's going to be some differences in, for instance, how we define the inverse operations. Okay. And so, some facts here. We have the commutative property, okay, for addition and for multiplication. So, doesn't matter what order I do these operations in, they are commutative. So both addition and multiplication are commutative. Okay, we have associativity. So associativity says it doesn't matter how I do the grouping. So it's not changing the order, it's changing which operations I do first in a string of at least 3. So for instance, if I add z1, z2 first and then add z3, that's actually the same as adding z2 and z3 first and then adding z1. Okay. And similarly, I can also, so multiplication is associative in the same way. So, so that's nice. All right. This is telling you your algebra is kind of at some like minimum badness level. Okay, you have a distributive property. So this is the interaction between the two operations, right? So if I have a complex number z and I multiply that by a sum, z1 plus z2, this follows a distributive property, or I can distribute that multiplication across the elements in the sum. Okay. All right. As the textbook points out, the fact that you have commutative multiplication means that, for instance, I y is the same thing as yi. And so whenever you have a complex number here written as x plus iy, you could write it as x plus yi. Right? Some people like to have the real number in front of the I, and it doesn't really matter. Okay, so that's just formatting preference then. Okay, and so of course having associative laws is nice because it means there's no ambiguity in doing triple sums or triple products, and so we can drop unnecessary parentheses here and just, it's not ambiguous at all to write. So, writing like a quadruple product like this is perfectly fine. You don't have to ask which product you're doing first here, right? So that's a nice thing about the associative property. Okay, so in terms of algebraic objects of interest, second you have two operations. You like talking about identity elements for those operations. So there's an additive identity, and it is unique. So what is an additive identity? It is an element such that when you add it to any generic element, it returns just that generic element, right? And so the additive identity is 0, or the ordered pair 0, 0. Okay, and so to show that it's the additive identity, if I take generic complex number and I add 0, right, this is ordered pair xy plus 0, 0, which of course is just the ordered pair xy, which is z. So adding 0 to any complex number returns complex number. I have a multiplicative identity. Okay, which is 1, which is, the usual multiplicative identity for the reals. Okay, so again, I'm not going to write it out this time, and I'm actually going to stick to that. You can, if you follow the formula, right, z times 1 is equal to z for any complex number z. Okay. Well, the second you have identity elements for operations, now you can talk about inverses for those operations. So inverse elements are elements that you can add to a given element to make it equal to the identity element for that operation. So the additive identity, if I add it to z, right? So if I add the additive identity to z, I should get the, or sorry, if I add the additive inverse to z, I should get the additive identity 0 here, right? And so I'm looking for a complex number, right? So z plus something is equal to the additive identity 0. So what is that something? Well, if z is complex number xy, then this question mark should be minus x minus y, right? And you can just check, of course, yourself when you add those together that you do in fact get 0, 0. Okay, we don't have to convince ourselves too hard of that. So then the additive inverse of z, which is xy, is, we'll call it minus z, right? Which is minus x minus y. Okay, so that's good. All right, what about the multiplicative inverse? Well, this is a little trickier, right? So to find the multiplicative inverse, what I'm looking for is I multiply complex number by something, question mark, and I get 1. All right, the multiplicative identity. Okay, so then what is this question mark? Well, it's a little trickier. Well, what do I want, right? So what I'm looking for, if I let, say, the question mark be uv, right? Then if I write this out in terms of what these things are, so if I rewrite this equation slightly, this is xy times uv, and that must be equal to 1, which written as an ordered pair is 1, 0. Okay. All right, well, what is this? Let's pull up our trusty formula that defines what multiplication looks like. So then here, when I multiply these together, right, I would get the first two slots, so x times u. So x times u minus y times v. Okay. And then I would get y times u plus x times v. Right? And that has to be equal to 1, 0. Well, if two complex numbers are equal, it means their real and imaginary parts are equal. So this gives me two equations. Xu minus yv is equal to 1, and yu plus xv is equal to 0. So I get a system of equations that I want to solve for u and v. Okay. So what happens when I solve that for u and v? Well, I again will let you actually check this on your own. That what you get is that u must be x over x squared plus y squared, and v must be minus y over x squared plus y squared. Now you inherently notice something here, right? I've got some things showing up in a denominator, right? So naturally, I want to require that this quantity be non-zero. But if x squared plus y squared is equal to 0, what's the only time that can happen? Right? Well, the only time that could happen is if both x and y are simultaneously 0. And so excluding that possibility is the same as excluding that xy is 0, 0, which is the same as excluding 0. And so finding the additive or the multiplicative inverse is only going to be possible for non-zero elements. But hey, that's perfectly fine because that's how it works for the reals too, right? So only non-zero real numbers, uh, you know, only non-zero real numbers actually have multiplicative inverses, so it's nothing crazy. All right, and so rewriting this slightly. So for non-zero z, the multiplicative inverse, z inverse, is the ordered pair x over x squared plus y squared minus y over x squared plus y squared. Or written another way, of course, if I have x plus iy inverse, that is x over x squared plus y squared minus I times y over x squared plus y squared. Okay. Okay. But I have this for every non-zero z. So as long as z is non-zero, I have a formula for the multiplicative inverse. So every complex number that is not zero has a multiplicative inverse. Every complex number, whether it's zero or not, has an additive inverse. Okay, and so with all of these additional properties that we've shown, what we have shown here is that the complex plane or the complex numbers define what's called a field. So I'm not going to get into exactly what that means, but this says that C is a field. If you want to look into what a mathematical field is, then you can. But basically, it's an extremely nice algebraic object. It's one of the nicest objects you can basically be dealing with. So another example of a field is the reals, right? So R is another example of a field. Okay. And so a lot of the properties of the real numbers that that you find to be very, very nice are actually these field axioms, is what they're called. Okay, and so there's a list of axioms that have satisfied a set equipped with two binary operations, addition and multiplication, are a field, and that's exactly what I mean when I say that. So anyway, so we've shown something really nice here. So there's another thing, another very beneficial fact that is true for the complex numbers, which is whenever you have a product of, say, two complex numbers, and that product of complex numbers is 0, well, what this means is that one of them must be 0. Okay, and so if z1 times z2 is equal to 0, this implies z1 is 0 or z2 is 0. Okay, so one of them must be. Okay. This is not a thing that is true, for instance, in general. So you have encountered things likely objects that don't satisfy this for a type of product. So for instance, matrices, right? You could probably in your head come up quickly with some matrices that you take two matrices, neither of them are 0, you multiply them together and you get the 0 matrix. So for instance, matrix multiplication fails this kind of thing typically, but this is the sort of thing that you're used to from the reals. And so how do I know that? Well, suppose that one of them's not, right? So suppose, say, z sub 2 is not 0, right? Well, then z sub 2 inverse exists. Right? Thus, I would have 0 is equal to z sub 1 times z sub 2, which implies that 0 times z sub 2 inverse is equal to z sub 1, z sub 2 times z sub 2 inverse. Now, by the associative property, of course, I can do this multiplication. First, 0 times any complex number is 0. We've already shown that. So then I have 0 is equal to z sub 1 times z sub 2 times z sub 2 inverse, of course, is 1. And z sub 1 times 1 is z sub 1. And so z sub 1 is 0. Of course, the only assumption here I made is that z sub 2 is not 0. So suppose z sub 2 is 0. Well, then one of them is 0, right? So one of these things has to be 0, and this is a quick proof of it, just directly from the fact that you have multiplicative inverses. Okay, and so the contrapositive of this, if you like, is that if z sub 1 and z sub 2 are non-zero, let me rewrite that on a different page. So the implication here is z sub 1 and z sub 2 are non-zero, then their product, z sub 1 times z sub 2, is non-zero. Again, these are properties that maybe you take for granted for the reals. We're just checking to make sure that the complex numbers satisfy this as well. Okay. All right. So then quickly here, let's rewrite, as we do also for the reals, let's rewrite these operations of plus and multiplication in terms of the inverse operations, right? So we know that in a sense, right, subtracting and dividing don't really exist. They're just notions that come out of it adding and multiplying, right? But it is useful, of course, to talk about subtracting two complex numbers. Of course, exactly what that means is just adding the additive inverse of z2, for instance, right? Similarly, dividing two complex numbers, well, that's just multiplying by the multiplicative inverse, right? Or of course, we can't have this z sub 2 being 0, right? So the thing in the denominator has to be non-zero. Okay, so here's, if you like, you can think about these as the operations of subtraction and division, but of course there's nothing actually going on there that isn't just adding and multiplying. Okay, and so let's rewrite some of these things in terms of our notation that you're more accustomed to. So let's say let's take z sub 1, rewrite this as x sub 1 plus I y sub 1, and z sub 2 will be x sub 2 plus I y sub 2. Okay. So then I want to be able to quickly compute these things in terms of the x's and y's here. So how can I do that? Well, z sub 1 minus z sub 2, of course, is pretty easy. I'm just subtracting the real parts, right? In that order. Right, so x sub 1 minus x sub 2 plus I times y sub 1 minus y sub 2. So that's fairly simple. Okay. Then if I want to write the division of two complex numbers, z sub 1 and z sub 2, then from my previous formula, this is just going to be, in fact, I think I actually wrote it on the, right, yeah, so I think I wrote it here in terms of x and y. Okay, so from this fact here, this is going to be x sub 1 times x sub 2. So this is going to be x sub 1 times x sub 2 plus y sub 1 times y sub 2 over x squared, x sub 2 squared plus y sub 2 squared, plus I times y sub 1 x sub 2 minus x sub 1 y sub 2 over x sub 2 squared plus y sub 2 squared. Okay, so I'm combining, right, my formula for product together with this formula for multiplicative inverse here. Now that looks like a really complicated expression here, kind of hard to actually remember this off the top of your head. But this actually has a really, really simple way that you arrive at this formula. And it's actually the way that I always divide complex numbers. So there's a trick here. So what is the trick? So the trick to dividing complex numbers kind of in a convenient way. If you have two complex numbers and you're dividing z1 divided by z2, this is actually the same as so taking x1 plus I y sub 1 over x sub 2 plus I y sub 2 and multiplying in top and bottom by this with a minus sign replaced here. Now this is a hint that what's going on here has an actual simpler way of expressing some of these things, but this will do it. And it's going to be an exercise that I give you in your first homework to actually check. So exercise, check that this gives you the same. So check that this is the same as the previous formula. Okay. All right. So as I said, this is a big hint that there's something going on here that it actually gives you a way of expressing some of these things kind of in a much more neat way. And so a lot of you that have already experienced this might notice already that this thing that I've written here has a name that we'll talk about shortly. Okay, so I don't see any more questions in the chat, so I will continue on. Okay, continuing, right, if I wanted to, for instance, use this property to, so textbook does a good example here, so might as well do an example of this here. So let's do the division 4 plus I divided by 2 minus 3i. Okay, so using this trick here, this would be 4 plus I times 2 plus 3i over 2 minus 3i times 2 plus 3i. Okay, and so let's quickly do this. So I'm going to do this multiplication out here. So what do I get? I'm going to get, so in the first and the last terms, I would get 4 times 2, and then I'm going to get I times 3i. So that's going to be 3i squared, which is minus 3. So I would have 8 minus 3, which is 5. Okay, and then the mixed terms are going to give me 2i and 12i, so that's 14i. So 5 plus 14i divided by, here I have 2 times 2 and minus 3i times plus 3i. This is some difference of squares business that's going on here, because these are the same things except with plus and minus here, the mixed terms cancel out, so I only get the pure terms, if you like. I get 2 times 2, and I get minus 3i times plus 3i. So I get minus 9i squared and plus 4. But minus 9i squared is 9, so that's 9 plus 4, so that's 13 here. Okay, and so if you like, this is 5 13ths plus 14 13ths I. Okay, so this is the complex number that results from doing this division. Okay, and so it's good to just give yourself a few practice problems to go through with this, because you're going to be doing this a lot in your computations going forward. You're going to be doing a lot of algebra that involves these things. Okay. All right. So, of course, there's a lot of things that we take for granted here about the reals that we have to actually check and make sure it's true for the complex number. So, of course, it's just a notational thing that when I write 1 over a complex number z1, that is really the same thing as the multiplicative inverse of z1. Okay, I'm just using this my definition of division here being this product by the multiplicative inverse here. So it's a product with 1. And so, of course, when I write something like z1 over z2, right? When I write something like that, that's actually the same as z1 times 1 over z2. Okay. And so the usual way of dealing with fractions that we use for reals works in this way. Similarly, right, if I were to multiply two fractions involving complex numbers like this, right, this works out in exactly the way that you would expect here, just due to how we are dealing with this notation here. So this would be, z1 inverse and z2 inverse, right, which is the same as z1, z2 inverse, which is 1 over z1, z2. And so I can do all of the usual ways of dealing with fractions that I did for the reals. I can do these, where now my inverse, my way of finding the inverse, right, explicitly is a little different, but algebraically it behaves exactly the same. Okay. All right, so then lastly, if I have two fractions, so we'll say z1, z2, and I multiply this by another fraction, z3, z4, then this is the same as multiplying the denominators dividing by multiplying multiplying the numerators divided by multiplying the denominators. All of these facts work out in the same way, and you can actually check that just directly from the formulas. Okay. Expanding a binomial, right, involving complex numbers follows the binomial formula in the same way that it does for reals. So if I have, and you can do this by induction if you like. So if I have z1 plus z2 raised to some power n, this expansion can be given in terms of Pascal's triangle, right? Just like it was for binomials involving real things. So this is the sum from k equals 0 to n of the binomial coefficient n choose k of z sub 1 to the k times z sub 2 to the n minus k. Right. So n here is allowed to be 1, 2, 3, 4. It can be any natural number here. N choose k is the usual binomial coefficient, so n choose k is n factorial over k factorial times n minus k factorial. All right, found via Pascal's triangle, if you like. Okay. All right. So any questions about that? Okay. And so we are getting close to reformulating some of these things into concepts that are maybe more familiar, or maybe even the way that you originally dealt with complex numbers here. So we're going to tie all of this stuff together. So this is, you can consider this portion of the course just a little bit of bookkeeping on these basic properties. And so let's return to our notion of the complex plane here. Well, I have complex plane and I have a complex number in the complex plane. Let me go get my straight edge, because otherwise I'm going to make my pictures look an order of magnitude worse than they have to. So if this is my complex number xy, of course, maybe I have it just written x plus iy, however you want to write it in your complex number out. The second you have a point in the plane, of course, you can think about that point as being associated to a vector emanating from the origin. Now, of course, there's a thing here. I said think about the point being associated to a vector. I could have just as easily said think about the vector being associated to the point that it points to, right, emanating from the origin. And because you know already that vectors and points are interchangeable here, right? So of course, vectors in the plane and points in the plane are entirely interchangeable. It doesn't matter which of those objects you're talking about. It's really the same. It's really the same thing. Okay. And so, for instance, right, here's just a few examples. Let's look at minus, we'll say minus 1, minus 2, right? So here's, let's see, minus 1, minus 2 would be this vector, maybe. Looks something like this. So here is the vector associated to minus 1, minus 2, I. Okay, let's do minus 2, 4. All right, it might look something like that. So here's minus 2 plus 4, I. Okay, if I just look at I, right, it's this vector. Okay, here's I, or 0 plus I times 1, right? Okay. All right, so there's some of my sample complex numbers viewed as vectors. What is the benefit here? Well, as before when you dealt with vectors, now there's some interesting geometric notions that arise out of this. So for instance, if you view them as vectors, when you think about two vectors given to you by two complex numbers, so we'll say here's z1, right? So this point is z1, and we'll say that this point is z2. Then z1 plus z2 has this following geometric interpretation, which you've no doubt seen either in Calc 3 or linear algebra or some other place, which if you think about taking z2 and sliding it along the vector z1, then where it points at the end, right, is what I can think about as being my terminal point of a vector that is this diagonal of the parallelogram that I've just completed here. So let me draw in this parallelogram here. This diagonal of the parallelogram is z1 plus z2. Okay, this was one of the alternative, interpretations of vector addition that you encountered when you first studied vectors in the plane, right? So this addition of complex numbers here actually just becomes the same as vector addition, okay, which has this parallelogram property, if you like. Quick exercise for you if you want. What's an easy way of describing the other the other diagonal of this parallelogram. So you can tell me in the chat if you want to. But yeah, and of course it matters in what order. It matters where the arrow is pointing, whether it's pointing from Z1 to Z2 or Z2 to Z1. But yeah, there's a geometric interpretation of both diagonals of that parallelogram in vector algebra. Okay. So why would we do this? Why would we bring vectors into this? So geometrically, vectors have what are vectors first of all, right? So vectors have two parameters that matter. Right? Literally, vectors are two pieces of data. They are a length and they're a direction. Right? So vectors are length and direction. So they're length plus direction. That is literally all the data that a vector encodes. Okay, and so if you have two vectors and they have the same length and the same direction, they are the same vector. Okay, and so, which is why, we can, without loss of generality, always assume that a vector is emanating from the origin, because if you take that same vector and shift it somewhere else in the plane, it's actually still conveying the exact same amount of data that we're interested in. Okay. And so vectors have length and direction. So what I'm really going to be interested in here is length. Okay, because that is going to introduce me to a concept that we haven't quite mentioned yet, which is the length of an associated vector here. Right? So I'm going to redraw my picture yet again so that I have a nice clean picture. So I have a point that is representing my complex number z, which is, of course, given to me by ordered pair xy. So I have a vector emanating from the origin, right, associated to that. I can talk about the length of that vector. Okay, now I'm calling the vector z. I'm using the exact same notation for the vector as the point because they're interchangeable. Okay, so then I can define the length of the vector z. Okay, that is going to be represented by absolute value signs here. So the length of the vector z, that is just the distance from xy to the origin, 0, 0, right? But what is the distance from the point xy to the origin, right, to 0, 0? Well, it's the square root of x squared plus y squared. This is called the modulus of a complex number z. Okay. All right. And it is exactly this notion. So the modulus of a complex number is really just the length of the vector in the plane determined by that complex number. Okay. So what is something to note here? So note the modulus of 0 is 0. So this is our first thing. Second, if z is real, so that is z is, say, x0, right, for some real number x, then the modulus of z is equal to the square root of x squared plus 0 squared, which is the square root of x squared, which is a fancy way of just writing absolute value of x. And so modulus is just absolute value. which is one nice way of motivating like why we just use the absolute value sign for it. When z is a real number, it's just the absolute value. Okay. Okay. Three, the modulus allows us to compare complex numbers. Maybe I'll put that in quotes. So, near the beginning of lecture, I noticed that, or I remarked that something like this, right, makes no sense. So a question, is a complex number less than some other complex number? That has no meaning. All right, there's not a notion of an ordering on the complex numbers in that way. Okay, but with modulus, it absolutely makes perfect sense to have a statement that looks like this, right? So in fact, if this is true, what would that mean? It would mean that if you plotted these 2 points in the plane, then this point is closer to the origin than that one, right? So it would give us some notion of talking about, relative size or relative distance of complex numbers, right? Now we're still not going to have a way of ordering these like we do in the reals. But like, why is it that this can be said and this has meaning, but this doesn't? Well, because the modulus is real, right? That's the key thing here, right? So modulus of a complex number is always a real number. And there's nothing that deep going on here. Just look at its definition. The x is the real part of z. Y is the imaginary part of z. Both of those are real. And I'm taking the square root of a real number squared plus another real number squared. So there's no way this quantity can be anything but real. Okay. All right. So I think I am out of time for now. We're almost on the cusp of being able to clean up some of that earlier stuff we did and make some of this notation a little bit more convenient. But I think this is a good stopping point. So this is basically how lectures are going to go. Since you're going to have pretty frequent homework, it's a good idea that if you have questions about the homework, bring them to lecture. You can type them into chat. Any questions, obviously, you have while I'm going on, just type them into chat, and I will answer them. Also, look at the announcement for your daily Zoom tutoring sessions that are there for your benefit. So have a look at those. I will update the syllabus page sometime before tomorrow, and I'll let you know when I do, so that you can have a quick look at that to see how the grade breakdown and all that stuff is going to work. But yeah, this is how the course is going to go. So your first homework assignment will be assigned tomorrow. You'll have a couple days to do it, and so this is how it's going to go. It's going to be pretty rapid fire. You know how summer courses are. So anyway, I will see you all tomorrow, same time.